bosses. But yes, you keep on learning. You keep on learning from your mistakes, and then don't repeat your mistakes at later date when you have learned this thing in your and whatever you learn by your height to your heart, and enjoy what is learning. Enjoy the engineering behind the whole thing. Now let's get into the little deeper into the whole thing, what we have today, the outline of the presentation today. What you can understand is the how to understand a structure, and then the basic loads, that there are so many of loads which you can, with some of them we can anticipate, some of them what we cannot anticipate. For example, the WTC, the World Trade Center, before that explosion, nobody could understand that, even imagine even that an explosion can pull down the entire building together. So that was a learning from our side. So that load, that is an explosion load, that is that explosion load has now come into picture while designing pretty tall buildings and important buildings. So, but today we are not getting into the too much of the details of it, but the basic loads that we are going to do, and the specifically the lateral loads and what is their effect, some very brief codal guidelines into it, and of course the lateral loads, we all know that the basic things are the earthquake and the mostly wind. So what are the damages that you can understand, while discomfort and damages that happen during an earthquake and a wind. Next slide, please. Next slide, please, Ankit. Now, to understand a structure, uh, the basic things that you must understand is the geometry, whether it's a rectangular building, whether it's a slender building. It's a very, the slender can be two, can have a two definitions. The width is small, the length is small, that can also be a slender. And the width is small and it's very tall, that can also be a slender. And both of these adversities can get into trouble in designing the building. And type of the building, whether it's a tall building, whether it's a short building, whether it's a mid-level building. So that second, the third point is also covering that thing, the height of the building. Then again comes the irregularities of the in plan and elevation. See, architects throughout the world, they design fancy buildings, and with them they make some of the buildings are even amoebic shapes. So you have a lot of problem in designing those things in specifically in the lateral load context. And what is the nature of the use? How are you going to use this building? Whether it's a residential building, then there is something which you need to consider while designing. The loading pattern also changes in residential, commercial, industrial, and the recent one, which we are all, it was there also, but recently what we are all stressing is the disaster shelter, which is becoming very common. How to this see, if you experience this cyclone, and sometime we also get into earthquake, very severe damages, then where do people will stay at when these damages happen? So disaster shelter is also a very nowadays becoming very common, and we need to take care of the loading. So, and any other special criteria that has to come up. See, I remember long back the present British Deputy High Commissioner building in Calcutta, it was given to us that any of the column in the building can get demolished due to explosion, but still the building had to stand for at least 5 to 6 hours. So that was the challenge. So one of the challenges that we had to take. Hope I'm clear in my voice, right? Anyway,
Your voice
so
is cracking a bit.
now,
I mean,
is it okay now?
yes, better now.
Is it okay? So now some of the modern, just take two pictures. There's so many of them. One is this rotating tower, which is come to you, many of you, through WhatsApp. So this there is a core rotating around it, which is a marvel. I haven't gone into the total details of it, but it must be a very marvelous thing that has our engineers in this world has achieved this, and and I would take a little bit of time in this. The second one, this forum atmosphere. I don't know many of you. I don't know whether you have are knowing about it or not. This structure from our own city has been shown in the has been displayed in the National Geography as an important structure. It is because there is a 100-meter bridge that you can see in the picture. It's there sitting on at a 100-meter level between the two buildings. Now it has a huge challenge in designing, because the forces, and this bridge is no matter a light bridge, it's a huge bridge. It's a 3-level deck bridge. It contains all the swimming pool, it contains all the soil fill, it contains 3 levels of amenities, etc. So it's the load inside is quite huge, and this is sitting on the terrace of the building at 100 meters. Now the very interesting thing is anyway, it becomes an altogether a different presentation altogether with this project. But I would say, guys, that this was an engineering marvel, and the best isolation of has been adopted in this. I would explain a little bit on this base isolation also later on, so don't get worried about it. Base isolation was adopted in this thing to take care of the forces, by virtue of which this bridge on that level can move in any direction by 250 millimeter, which is about 10 inches. So yes, in this city we have achieved this thing, and I take a little pride of that with all my colleagues and engineers and all. Now if you see the different load that we acts on structures, you can see the gravity load, which is a dead load, live load, and the lateral load, that is the wind load and seismic load. There is a temperature load. I don't know whether many of you can understand, but class 12 physics, if you go into the class 12 physics, if there is a linear, there is something which is, there is a difference of temperature, it linearly expands or contracts. So that can also happen to your building, and for that matter, you have to take precautions into it. And for that matter, if in your code, there is a provision of providing expansion joint. If there is a much more expansion or there is much more contraction, so you need to provide an expansion joint so that it's not affecting your structure too much. Now comes this impact load. This is an explosion load that I was talking of. And in colder countries, you can understand the snow load is also pose a lot of problem in the winters. There's a huge heap of snow on top of it. If you are not having a slope roof, then it's a huge load that you have to handle. So now the basic load distribution that you can understand, see from the picture, that the gravity load, how it moves down. It's a vertical direction to the it's a all gravitational force which is attracting all the loads down to the earth. So and in the second picture, you can see that the wind load, how it happens, that there is internal pressure, there is external pressure, there is suction, and there is suction on the uplift. So all these things comes up. And the third one is how a seismic behaves. See the dotted line. We can see a dotted line in the picture, and how the building, why there is a ground movement. I will explain you a bit of this, because this is important, that where I find many of you can't really visualize what an earthquake is. So there is a ground movement, and the dotted line is your initial position of the building, and the building moves in that direction. So what is basically, again, in this slide, you can see that how load flow happens in the gravity. See, the dead load on the floor, dead load, live load on the floor, from the slab and beam to the column, how it comes, it's a horizontal flow. And how do you do it? And that is where the deflection and the flexural design comes. So that has to be this beams and the slab has to take the oh, Ankit, it's not showing in Helena's screen. Can you just have a look? Is
It
it
is
okay
showing.
now?
It is showing. It is showing.
Okay, fine. So, so
Hmm.
see the load flow path when it is horizontal, so that then the deflection. So when I also tell you, boys and girls, that when you design a slab, take care of the deflection. That is the major. Flexure is also, of course, a part, but take only thing, because it's a thin element, and it has to take care of the load and transmit it to the beam, which has a deeper depth. So the deflection in beam is not really too much of a criteria, but flexure and shear is in a beam. So put it in your heart that while designing a slab, deflection and flexure is the design criteria. And while designing a beam, flexure, shear, deflection, yes, when it's a very large beam, when there is a too much of a load into it, there is, but normally speaking, flexure and shear is the criteria for designing beam. Now, regarding the column, you can always see that is the axial load, that is compression load, that is the design criteria, and shear is of course a criteria in lateral loads. But basically, a column is to take care of the compression and bearing of, that is the load coming from the column. It's at a at a level where the soil can sustain the load. That is the function of the
What is
foundation.
this HVAC? What is HVAC?
HVAC is equipment. We just meant HVAC is equipments for your air conditioning. So heating,
Okay.
ventilation, air conditioning. So that's HVAC. It's just a notional, so that you know how the equipment load also comes into place. That's how it's shown. Don't get
Okay.
too much into it. That's just an equipment. Okay, next slide.
Oh,
So the first, the lateral load. Now, to experience a lateral load, we first thought of explaining a little bit on the wind part of it, and then. But wind is, because wind is a little bit of an easier thing to digest rather than earthquake. I at this age also, you know, I still have some doubts in my mind regarding earthquakes, but still visualize that there it is a load, which is, as I say, that if there is a load, there is a deformation, and the deformation is in the direction. Uh, can you hear me now? Is it okay now? Okay. So wind is much easier to understand, but there are certain things which you will understand. The statical part of the wind is, of course, easier to understand, that there is a wind in one direction that is coming, so the building or the structure is going to deflect in that direction. But as I said earlier in the beginning, it's not always true. So let's go into the other things so that we can understand each of them, because there is a time constraint also. So there are a lot of things which needs to be done. Now, how this you you know about this thing, but still you 10 class 8, 9, 10 in geography, how there are the prevailing winds on the surface towards the equatorial region, and how the seasonal winds happen. So this is in the warmer, from the sea in the summertime, from the sea the cooler air comes to the land, and in the winter times the land to the sea. So this is what happens. This is the seasonal wind, and which I think the cyclonic wind and the typhoons, the other things that have all seen. You have all seen the recently the Amphan that has come, how devastating it can be in but this is a local wind. This happens, you know, this is not the cyclonic wind. It's not a very regular phenomenon. This is not a very at all a regular phenomenon. It happens at times, but it can go do a devastation at that time. You know, your structure has to be safe, and not only the structures, the facade, the glasses, the windows, the other things has to be safe. You can have seen that so many of glasses have come down, so many of glasses have broken due to this. So we have to we the structural engineers have to deal with this also. Next slide, please. Now, next slide, please. Yeah. Now, how a wind flows, you know, uh, there are so many of 12 pictures, 12 sketches. Most shows the all types of winds that happens. This is the first one is a structure standing tall amidst very low rise structures. So you have wind flowing on the roof, you have wind flowing on the sides, and you have wind flowing on the ground. Now this ground wind, which I will explain you a little bit more on this creates at times a little problem. Now, the second one is where you have it's a very typical city, congested city condition, where a city like New York or a city like Mumbai, where you have so many of tall structures down there, and mostly the winds are all shielded, so it's just flowing on the top of it. Now the third one is where I was telling you about the ground. See how the wind happens. There is a wind which is directly facing your building, and then it's going down, and it can create an havoc in the people moving on the ground, and we call it an upskirt effect. And it can ground pedestrian discomfort can happen due to this people walking all around. I think these are the things which you should always experience in life. Say for example, in a tall building, there is a tall building, you just walk around it, you can feel what I'm saying, that this is very windy at the bottom. Why is it so? Because of this third phenomenon. So we have to, and tall building, tall, see, we in our city we don't have a too much of a tall building, but in other cities this can create an havoc. People cannot walk around the building even if you are not taking care of it. And the fourth one is the tunneling effect, and the fifth one is if they strategically placed, the wind forces can be very less. But if this one, the other one, the next one is there can be forces amplification. Now the shape of the building, as I said earlier, how it happens, how it helps. If there is a shape of like this faceted building or a circular building, the wind deflects and not affecting too much into this thing. Now there are some codal guidelines into this thing, 875.3. Many of you have seen this code, and this is the thing that the formulas that has been given is basically a static wind. Static wind is, as I said, the load is coming, the deflection is in the direction of the load. And when the load is withdrawn, the building is to its original position. So that is called the static wind. So this is the formula that, in fact, many of you have gone through it. So the second one, this PD, you can see this PD in the formula, F equal to CPA minus CPI into A into PD. This PD is the design pressure wind. Now this PD, as per the code, it has been modified due to various factors like the location, the terrain, importance of the structure, type of the structures, K1, K2. So all sorts of parameters are there, which are that the code has realistically tried to see what is the code. Now this wind speed and what they have done. They have taken, and these are all statistical. You never know that the next second there can be a huge earthquake which is beyond this codal provision. There can be huge wind speed which is beyond this capacity of the code. So, but they have taken a statistical, and the codal provisions regarding these lateral loads are mostly statistical. And also they tell about some 50 years return period, 100 years return period. What that does mean is that within that 50 period, the most probable wind speed will be like this. The most probable earthquake forces will be like this. Now, as I was telling you about this thing, is the dynamic wind. Now, I'm just giving a glimpse. Again, don't get this is not at all a very complex thing. Yes, it's a complex mathematically, but first, before getting to the mathematics, it is very important to understand what is the phenomenon of dynamic wind and turbulence and vortex. Now, in an aeronautical engineering, wind coming to on a surface, it rise to three forces and moments in three directions. In aeronautical engineering, the uplift and yawning is very important because it lifts. But in our case, as a structural engineer, the two directional wind is very important. Now, in the second picture, which I was trying to tell you that why the wind dynamics is very important, is see the wind is coming on this one direction. There can be some structural geometry, there can configuration which can also swing the building in the other direction. Yes, that can happen, and that depends upon the shape of the structure, and that depends upon the wind speed, and that upon the nature of the wind also. But that is what is the dynamics of wind. So the wind direction is happening in the straight in one direction, but the deflection is happening on the other direction. That we call a crosswind phenomenon. Next, please. Now, in this, while understanding the this dynamics, also now understand these terms. You will some of the you also get into details of it, but at later on. But just understand this thing. Turbulence and vortex. See the pictures. The wind has come. Depending upon the shape of the building, there will be eddies on the edges, which are called vortices. Now, these eddies will continuously move on the surface of the building, and the building, as you can see, the building is deflecting on the other direction, but the wind direction is thing. So this is a vortex which can create a deflection on the other direction, and we call it a crosswind oscillation. Similarly, this vortex can happen to, and there is a podium in between the two buildings. You can find it very windy. If you Ankit, if you can go to the previous and two slides earlier, the slide earlier. Yeah. Now, if you go to the fourth picture, see in the ground, you can, what I was trying to tell you, there is a tunnel inside. Now, you again, I would say tunnel. There is a driveway. There is a driveway. Now, you experience these things when you go into a driveways of some high-rise buildings. You will find that is the very high velocity wind coming, very windy, and so because the wind is coming a very small opening there, and then again out into a vast expanse, so that there the wind velocity is very high. So this is an experience which if you have some things which are on the face of this can get damages, so you have to take care of this. Now, okay, yeah. Now, the effect of the geometry, which also takes care of the, as I also earlier said, also takes care of a lot into the wind effect of the building. For example, in a circular and a rhombical shaped building, wind comes and flows on the sides. It doesn't affect too much into the building. But when you have, and the third picture from the top, you see the building. There is vortices at the bottom. There will vortices at the sides, and all sorts of things will happen if there's a little longish building. But these rectangular buildings are very common, and so the shape of the building, the geometry of the building, and the aspect ratio of the building plays a big role in understanding the effects of the wind. Next slide, please. Now, this is a very important picture that I want to understand. You must understand all. As I said, the along wind and crosswind I have already explained to you. Now, you must look into very carefully the third figure. Now, this third figure, the thing that till now, whatever you have learned and whatever you have seen, there is a mean pressure, that is an average pressure. But when you see a wind condition, You must have experienced this, that this is that this wind is, especially the local wind condition what I'm talking of, it's not a very sustaining wind. So it can come in a very strong way, then in the next second it can lessen down, then again it will come. So that is called the gust. And you can see in the picture there are apexes there from the dotted line. So these gusts and the peaks, these are uh, very harmful, I would say. And if not designed correctly, then you can find, as you have seen, so many of damages that has happened recently in our city due to this cyclone. See, people are saying that there is, you must be hearing two kinds of wind pressures into this. One is somebody was saying, telling you 150 kilometers per hour. Somebody was telling you 120 kilometers per hour. What is the difference? What is the difference? These are the two factors, that figures that are coming to your mind. So this 120, 125 that is in, that we came to hear is the mean pressure at that time, average pressure. But 150 times it reached the peak, and that at that time of the peak, you have seen many of the sheds, many of the has been blown away. So this is important. You that when this gust is happening, the next second it is getting withdrawn, and the building is swaying from here to here. So there is what happened? Okay, okay. So there is an oscillation. There is an oscillation due to this gust. I hope you understand. Sorry. Uh, so you hope and you understood this phenomenon of gust and mean. Now this gust is again not a long-standing one. This is a short 3 second. We sometimes take 3 second gust. We take 5 second gust. We take 10 second gust. Depending upon the importance of the structure, we take these 3 second, 5 second. But normally we design for 3 second gust. And the figure that has been shown to you is almost a 3 second gust. Now, it. Now, yeah, Ankit, just next slide, please. Yeah. Now, this dynamic nature of the wind, this can you can see there are so many of zone 1, 2, zone 3, zone 4, zone 5, so many of the there are so many of zones. Now, zone 1 and zone 4, these are sustaining, where you get sustaining wind pressures, but at the corners you get much more the wind velocities, and the effect of the wind get magnified. So keeping aside this thing, you Ankit, get to the next slide. Let me explain, and then we'll come back to probably. Yes. Now, while I was explaining the gust and all, see the first picture that you can see, there is the building is swaying. So while this gust is happening, the building is swaying in one direction. The next second, this is going the other direction. Why? So while this oscillation is happening, there is an acceleration to this thing. So what is that acceleration? Which there are ways and means to calculate this acceleration. And this acceleration, you try to understand, if this acceleration is very high,
Your speaker is making some sound. If you could just adjust the wire, I think so.
oh, is it okay now?
Yeah, it's better, much better.
Okay.
And if you could keep your mic a little away from your mouthpiece, I mean, the mouthpiece away from your mouth, so it'll be
Okay. Okay. Is it
yeah,
okay now? Is it okay now?
absolutely,
Because at
absolutely.
times it was cracking. That's why I took it
Yeah,
in.
no, now it's
properly.
absolutely okay.
Okay. So now, this is, boys, this is very important phenomenon which I must tell you. This you must understand. This is a very important thing. I think physically this phenomenon has to be understood. During a gust, there is a wind pressure on one direction, and there will be a suction on this direction. So the building will sway from one direction to the other, and there will be acceleration. So this acceleration, again, if there is too much of acceleration, so people living there on the top can feel discomfort. And you must have heard that during the Amphan, many of the people have complained about this thing, that there is a discomfort and they felt this way, and they were feeling discomfort. Now, see, this cyclone and this high gust wind, this stayed about for 5 long hours. Now, during this time, there was swaying, there was, sorry. Okay. So there will be some discomfort, people living up there, which is of course a little discomfort. So how do you deal this discomfort? So this is a challenge to our structural engineers. Our code has recently added something to it, but previously it was not there. Very recently, our code has added to this. But codes like Canadian code, Australian code, American code, British code, they were all there, this discomfort, how to handle this thing. So what you need to do is, this acceleration is all dependent upon the deflection that is happening at the top during the gust. So you need to control the deflection. All this is, you need to control the deflection. How do you control the deflection? You control the deflection by adding the stiffness to your building. So that the deflection at the top is not that much. So your acceleration during the peak gust is not that much. So there is a what should I say, a parameter to how to control, how to understand this discomfort. We normally in residential building, we call it a 1.5% of your gravitational acceleration. That is 1.5% of your gravitational acceleration. If the acceleration of the sway at the top due to this wind is 1.5%, then you can feel it. So your building has to be, acceleration of the building has to be a little lower than this. I hope I can get you some feeling about what I was trying to understand. But now you get into some textbooks and the codal provisions, then you can find a little clue much to it, because it's a vast subject, I tell you. Now the second one, the other one that I was talking about you sometime back, in some slides back, is about the pedestrian discomfort. Now in a tall building again, as I said, that wind is coming from one direction, and it is just on the surface of the building, hitting on the surface of the building. And this, what happens, some part of the wind gets directly downwards, some goes upwards, some goes to the sideways. Now the part that goes downward creates a problem. And then when again it goes down and hits your ground, you can try to understand this thing. This is also a little complicated, but you find very interesting into this thing. It hits the ground, and then when it hits the ground, then it again starts to go up. So this is, we call the previous slide, please. This is what we call the upskirt effect or the pedestrian discomfort. Now in tall building, I tell you, this can create, as I said earlier, you can feel any of your tall building, you just walk around a tall building, you can feel this, that it is very windy. Now there are ways to take care of that. We can shed off this. You can use canopies to break down this thing. Somebody, if you have been to Burj Khalifa, there are terraces on all levels, and at that level the wind is so strong, but while standing there you cannot feel this thing, because they have placed some wind deflectors at the top. So while this wind, as hitting the surface, going down and creating this upskirt effect, will not be understood. So during wind, this is the thing that we must understand very clearly. Now, as I was explaining you, that while we have been getting into the codal provisions, parameters, there's that the factors, terrain categories, etc., all are imaginative. So, for example, you are designing a building. You never know the next door neighbor can be a 35-story building, or maybe the next door land can be vacant. So, these are the things which you must understand while doing a design, and you cannot anticipate that these are the things which are coming in your way while they're designing. So very recent, it is now becoming a very common feature that we do a prototype wind tunnel test. What is a wind tunnel test? For example, you can see this building, this model. This is of the Atmosphere Kolkata building that was tested, wind tunnel tested, and you can see the model inside it. So what do? You scale down the entire building, and then there is a wind tunnel, and you you send wind there, and adding some structures here and there, so you can exactly understand what is the effect of the building. And more than this effect, you can also understand what is the, see, as I said, that these days there are too many of glasses that are going to come up. So once on the window panes, so your wind should not affect your glasses. So that is also we call a facade design. So this wind tunnel helps a lot in helping us in understanding the facade design.
Yeah, just like to add that India is one of the few countries where we have wind tunnel facility available. It's in the world, very few countries have this facility, and because of this
Yes.
facility in the Amphan, a lot of our buildings using this facility were term safe, and there was no human loss or life because of this detailed study.
Yes, I will also explain you in the next slide. Go to the next slide. I will tell you. Now, again, at times, as I said, when the human discomfort is too much, and there is a limit to your design also, how much stiff you will do, and then you have to, as an engineer, you also have to understand the economics of the project. If you become too expensive, the project will not happen. So we engineers all have to also think of the economics of the structure. So there comes a phenomenon called damper. What is a damper? The damper is that, I just tell you, it's a long, to cut a very long story short, it's a just to balance the deflection that will say, for example, if there is a mass there at the top and your building is deflecting the other way, the mass will deflect the other direction. So that will balance the movement of the building, and then the total deflection that we are anticipating will reduce to a great extent, and the oscillation acceleration that we were talking of will be reduced to a great extent. So these can help us in a lot in reducing the human in achieving the human comfort. Now, this, as Ankit said, that this wind tunnel test helped us a lot. While we were into this 42, which is the tallest structure in the Eastern India, 62-story building, we made the structure as much stiff as possible. But can anybody can imagine, in spite of that, how much it was deflecting at the top? It was deflecting at the top by a 1 feet, that is 300 millimeter. We could not stop it. And for that deflection, at the top, the sway at this moment, there was a discomfort. There was a discomfort that we were anticipating while designing. So what we did the wind tunnel study, and from that wind tunnel study, we came to understand that there can be a damper, which is a very simple damper. You can see these two tanks, one on the top of the other, which we call a twin damper, twin liquid damper, which we have put, and this has helped us in a lot. And in this high wind speed like Amphan that you have witnessed, nothing has happened in this building. So that is, yes, we feel a little pride to have this thing. Next slide, please. I think we are more or less, I have given you an overview of this wind. And this is the slide which is some of the disasters that you can find which has happened very recently, which can happen when wind. So just a clear understanding. I hope I can have given you a more of a overview of the how wind can, how you have to handle, how you have to, where you have to be very critical, where you have to be very particular, very careful while designing building for wind load conditions. Code is there, books are there for help you, but first of all, have the entire physics behind how the things are happening.
Just as Sir told, like if we design with whatever factors we told you, we explained you right now, whether it's Amphan or any kind of wind, there will be never a very severe structural damage if we follow the rules, books, and our physics, what we have learned. And whatever you see, the damages here are the things which have not been designed or as per nature's law, what we have learned.
Yes. And what is a design? I tell you, a basic principle of design, what I have learned for all these years is anticipating a damage, anticipating a failure. So this can happen. Can I see in the atmosphere Kolkata, there are certain things which we are not didn't anticipate in the beginning. So when the things were coming up, it was a very difficult task for us, but because it was the first time that we were doing something, some kind of thing like that. So we learned that these were the things that we did all of them, whatever we could do, but it was a little late, and we had to spend our nights together, unslept nights, to solve the problems. But at the end of the day, all of them have been sorted out. Yeah. Now the next devil that I would say still it is a devil to me. It's the earthquake. Yeah. Now, so what is the basics of earthquake? Again, while many of you, while sitting in front of me, while these young guys, what I found that the confusion between you all is, and I had also the same confusion, I tell you, that what is the basic difference between a wind and earthquake? While doing an analysis in a computer, when I have used this computer, I tell boys and girls again, do not depend upon the computer. I tell you again, do not depend upon the computer. Computer is just an helping tool. I find people saying that I know this software, I know that software. No, I don't rate as a structural engineer, high about a structural engineer, knowing the knowledge of a software. You must physically understand the structure. As I say, close your eyes and understand. Coming back to this earthquake. So the basic difference between, an earthquake, while analysis, you have found out that while doing an analysis, you have seen that both the things in computer, you have applied forces on the top and the building is swaying, and you have found out the forces into this thing. But try to imagine what is an earthquake. Is there any force on the superstructure? No, there is no force in the superstructure. There is a seismic wave that comes into the ground, and that moves the ground up. There is a movement in the ground. So the foundation moves, and class 10 physics, the Newton's laws of motion. By virtue of inertia, the head is static and our foot is moving. So this the class 8 we have learned class 8, 9, class 10 we learned the laws of Newton, which says that there will be an inertia. For this inertia, you tend to stay static, the upper part, while the bottom part moves. Now, while the second picture, second figure, if you see to it, you can see that the vertical elements as well as some of the horizontal elements, the vertical elements have bent. Now, in this bend, what has happened? The strain has been induced into all these vertical members, And what analysis we do? We do this analysis is that for inducing this strain, what is the force required? That is why what we do, we anticipate the amount of strain that is going to happen, and to get to that strain, just reverse the picture to the right. If you see the right side of the second figure, if you see, it's the same picture. If you have applied some load on the top, it is moving on the top. So this is what we do. We apply a load, which is, we call it a pseudo analysis, pseudo static analysis, by virtue of which the strain or the movement that is happening at the ground is simulated in the top by applying the force of the top. This is basically the understanding of the earthquake. There are ways the earthquakes, again I'm telling you, this is a static version of it. There can be dynamic, and the wind and the earthquake dynamics are much more complex. Even to this day, I am not clear about the very complex, but there are ways you can very, the design process is not that complicated. You keep your head cool, you can design well. Don't worry about it. Next slide, please. So this is what is how for some of the things where for which the earthquake depends upon it depends upon the mass, it depends upon the distance and magnitude from where the epicenter happens, it depends upon the soil, it depends upon the height of the building, it's depend upon the geometry, plan irregularity. Now, as I said, as you must be knowing this thing, if you have an irregular distribution of the mass, if you have the irregular distribution of the geometry, then the earthquake force gets amplified and aggravated. And of course, what is the framing system that you are adopting to the earthquake. Now, again, coming to the basic principles of earthquake and wind, I tell you, earthquake is, it happens for 12, 15 seconds, 20 seconds, a minute max to the max. Till this record, I think world recorded about maximum earthquake is about duration of earthquake is about 5 minutes, if I'm not wrong. I'm not too sure about the figure, but normally what we see 15 seconds, 20 seconds. Now, this is a time. This is very crucial, where as a designer, what you should understand that your structure has enough strength that it is not collapsing. At this time, during this time of that 12 to 15 time, you should not be too much worried about the deflection at the, yes, of course you must be, but not too much worried. You should see that your building is not collapsing. That is the fundamental difference between wind and earthquake. Is for a wind, you must see the serviceability, that how much the deflection is happening, how much the discomfort is happening to the human. But in earthquake is the strength. The building, you should be very careful that your building is not collapsing. So again, this, as I said, the Newton's first law of motion of inertia, that is the most important thing in understanding our earthquake. So you can see three of these things, where the force is mass into acceleration, which is equal to this, which is when the mass and acceleration is greater than the force, and this where the forces are much more greater than this thing, the inertia force. So next slide, please. So this is a Caudal provision static force. I think many of you are very acquainted with this thing. And this is, as I said, this pseudo-static analysis that we do. We apply forces and we get the deflection at the top as well as the forces at the ground, and we design this according to the requirement. Yes, next slide. Yes, now the devil. I tell you the devil. This is the dynamic earthquake analysis. Now, as you can understand, the seismic force that I have shown in the very first slide, this seismic wave I have shown it's one direction. I have shown, but these seismic waves will happen in all directions, X, Y, in even vertical. Vertical, we call it a rocking, and which is also a very, but thankfully that is not too much affecting our building. But yes, of course, we have to take a part of it. But the two lateral direction is much more vulnerable, and this happens together. It twists the building, and depending upon the structure and the mass distribution, the building can twist, the building can sway. So, and we are always very afraid of a twisting building. So while forming our structure, we have to be very careful that the basic structure, the fundamental time period. Again, many of you may not be aware of the fundamental time period. But I think you need to study, but don't worry about this thing, that I'm just giving an overview, that it's a lump mass and spring system, that is the equivalent to a mass and spring system that again, from the first law of motion, first law of motion, there is a mass there, and you have a vertical stand on which this thing happens. Now this vertical, if there is a damping ratio in the building, the building has an inherent factor, which if we replace the entire this thing by a spring, then an analogy can happen. See the effect of this building in this video. This is a real life building, and where the dynamic analysis has been done in this building, and the first mode of oscillation, how it is response of this structure, how it is happening, you can understand this thing. So it's a little, not, I would say this absolutely a translation, not absolutely a translation, but this is a little rotational, but little rotational is okay, but we'll try always to have a translation. You will understand when you go on to design much more structures, what are the difficulties in going for a torsion in the building, which aggravates the much more earthquake forces, and at times it becomes very difficult to handle those forces also. Next slide, please. Now, the concept of this thing is a P delta analysis. Again, I'm giving you a very overview of this thing. Now, when a building sways, when a building sways, still the forces are there, but on top of it, there is a deflection induced into the building. And so, for example, the building has swayed, and the forces are there on the top. There is an additional moment due to this delta deflection deformation, additional moment and other forces will come, which is very detrimental, and this is a much more additional force that will going to come up, and at times this can create havoc. So this base shear, this graph can show you. See, the first one is perfectly in the elastic zone. That is, when the force has come, it has deflected, and it has come perfectly to your original positions. And the second one, you see, it's not a crack, but you can see very minor thin cracks that has happened, and some minor permanent deformation has happened. Minor, very minor, I would say very minor. Then the third one, you can see there are cracks in the non-structural elements that has happened, and one or two of them you can see some cracks in the structural element also, but these are again not too much. This can be again revived into the original, but there is no matter whatever small it may be, there is a small permanent deformation also. Now the third one, well, there's a mass cracks in the building. There are some collapses in the non-structural elements, and this building is a dangerous, and we cannot, it is not a livable building. So we must demolish this building, and we redo the building, reconstruct this building. But the previous one, we can still stay with some retrofitting into it. We can keep it to its bring it back to its original structure. And the last one is the complete collapse. While doing this thing, the plastic hinges, while the cracks in the structural elements happens, the plastic hinges induce. So see, that is why I'm saying a P delta. Now, if you get into, you can understand, even when this building is in the sway, that the fourth figure, there you can see the building has swayed there, and still the forces are there into this building in the dead load forces, and this will sway it much more. And then if it doesn't have any capacity, then it will collapse. So that is the phenomenon of a P delta, and this is we called a nonlinear analysis, which is not linear, that not in the elastic zone anymore. But this nonlinear analysis is also a very important factor these days, because economics, as I said, economics, we should understand that what are the real forces that will going to come up, and for those forces, how my structure is going to behave in that particular force. That is very important to understand. It's a vast subject. I don't think I should make life difficult for you into this, but this is what is basically is. Now, that basic factors that controls how a building behave during earthquake forces, as I said earlier, yeah, next slide please. Yeah, the soil. In a bedrock situation, where there is very solid rock, mostly a rocking motion is very important. Lateral motions are there, but it's not that strong. But rocking motion is very important. In a soft soil condition, then rocking motion is not that much, but your lateral motions are much more, and they can amplify your structure too much, and then finally gives into your collapse. Next slide, please. This is self-explaining, how the deflection happens. Tall, short building, squat building, it can get much more forces, but the deflection is much less. But yes, a tall building, when it sways like that, although this is people may feel a little discomfort, but it will never collapse. But the chance of collapse of a shorter building in earthquake is much more. But this is absolutely reverse when you get into an wind condition. Next slide, please. So how this slide shows you how different geometries gives you in the dynamic condition how it behaves. L pattern, an L pattern, C pattern, a T pattern, how it behaves. So these are not not a very you can see the rotation is happening, the torsion is happening into this building. So these buildings. So at times, although this that we try to achieve with the structural system to get a translation, but these L-shaped and the C-shaped and the T-shaped are mostly prone to torsion, which we should try to avoid if possible. Now, defined framing system, as you see, moment framing, just column beam structure, you see how much it has swayed, and see how the pattern of the sway. It's just like a cantilever. Mostly a cantilever pattern. You call it a flexural mode of bending. The second one, when we have put some bracing into it, the deflection has settled down a lot more, reduced a little more, and the deflection is much more under control. And the third one, when we have a shear wall, see the pattern. It's a shear mode. We call it a shear mode, and the deflection at the top will come down much more. It will reduce. The more the shear wall you give into a building, in earthquake condition, the deflection and the deflection will definitely come down to a large extent. Bracing systems, as you know, these are the type of bracing system which can transfer load directly to the soil without disturbing too much into your structure, which can take down the entire load down to the ground by the bracing system without disturbing too much into your horizontal framing system and other framing system. And next one, please. Now, this is again a very important thing, how in a structure the slab behaves. Now, what is the function of a slab in a lateral load condition? Many of you will tell me that, well, it doesn't have too much of a role, but it has. We call it as a diaphragm. What is the purpose of it? This diaphragm will also determine the deflection of the sea. Each one of the the slab is very thin and it's a flexible one. So there you can see the deflections are not uniform. So this is what we also must understand, that, well, both of them are designable, but as a structural engineer, you must always try to have a rigid diaphragm, and mostly in a slab that we provide in our designs, that is 125 millimeter, 5 inches, 6 inches, 7 inches slab thickness, and cast in situ slabs are mostly provide a rigid diaphragm. But there can be cutouts in the slab. For example, there can be vent shaft, there can be pipe shafts, which discontinues the diaphragm, which you need to understand where these cutouts are happening. So there again, close your eyes and see what will be the load path and what are the columns will get affected by that cutout in the slab. Next slide, please. So this is the concept of the mode shapes, and this you can get in any of the textbook, that the lump mass and the spring mass system that I was talking of. Any dynamics book you can get it, but I'm just giving you an overview that what are the mode shapes that you fast translation motion that happens, that it's just so it's fast mode, and the second mode and the third mode, see how it happens. And these are all simulated by a lump mass, that is mass is m and the stiffnesses are k. So, and the right figure is the fundamental mode. The more the FEM analysis we do this thing, but previously we used to do a mass spring mass system to get a dynamic analysis of this thing. But these days we do a finite element analysis to understand the clear behavior of the structure. Yeah. Now, try to understand a collapse mechanism, how in the earthquake, some of the things which leads to the collapse of your structure. See, there are 4 such mechanisms which are very poor. For example, the columns are very weak at the ground, for example, and there the connection is not done properly. Then you see what happens, the building will sway in this direction, and there will be instability in your structure, which you will not like. The same thing goes to the second one also, and the third one also is a different kind of. The ground one is okay, but the top can go for a land. And the middle one, the central one, we call it, is a soft story situation. Soft story situation is what is very important, and while designing an earthquake, there is, if you have a very strong stiffened structure at the bottom and the upper story is weak, then there is always a possibility of getting a plastic hinge at that point, that what has been shown here, and then there can be a collapse. Rather, I would say the 2B picture, what you have, the columns are exercise and R&Ds with this. But we normally do not, while modeling a structure, we ignore this infill wall. But as you can understand, while there is a deformation, this walls and this thing infill wall can act as a strut and thereby give you much more stability, add much more stiffness to your building, and thereby it draws because a stiffer building, if you imagine, a stiffer building will attract much more force than a flexible building. So this, although it's an infill wall, we do not take a structural part of it, but this can be very, this can make the structure very stiff, and the anticipated base shear due to earthquake can be much more than what we have calculating. So there the codal provisions have given us much more that how to handle these situations. The codal provisions are there, but in our office we are trying to do some R&Ds. These guys, Ankit and all team, are doing some R&Ds that how to model these two in your structure, so that it's not possible practically to model all these things, but a little realistic feature, if you can have a little realistic feature into this thing. As I said, now try to understand, which is a very common thing in you can see in many buildings. In a ground, you have a parking bay where you don't have a wall. Now, in the upper stories, you have a wall. This is the most dangerous situation, and if you can see many of the buildings where in earthquake situation the failure has happened, you can see in the in many, you can see in many pictures in earthquake failure, that this is one of the major cause of concern in earthquake failure, that the stilt where you have the car parking and you don't have any brick wall is a soft story rather than it's a weaker story rather than the top one. So how to handle it? People will ask me that this is a very common thing. You have to put the cars in the ground. How to handle this thing? So what we will say that there are ways to handle it. You give some RCC walls or even brick walls, a little thicker brick walls at some places, so that the more or less the gap between the stiffness in the upper floors and the lower floors are lessened. Say, if we call it a soft story when the difference is about 30%. If you can lessen down to 10% maybe, then there shouldn't be too much of a worry. So at ground, you must put some walls to make it also some strong, keeping in your mind that the car parking is not affected, because that is also a very important thing in your building. As I earlier said, that strong column, see what happens in these two pictures, that a strong being weak column creates a plastic hinge in the column. A plastic hinge in the column will induce collapse too quickly rather than this one. So we should always stick to, in earthquake situation, in any structure, we should always try to understand that the column should be much more strong. There are, again, don't worry about it, how to calculate what is weak and what is strong. There is ample formulas in the code. There is all these things are defined in the books. I'm just giving you an overview that you must keep these things in your mind, and get to any textbook, you will find that how to handle this. Don't worry about it. And a little bit on the shear wall and a coupler, see, in a situation like this, there are shear walls, and a blank shear wall without any opening, you won't find too much of it. There has to be opening. There can be small opening, there can be short opening, there can be very large opening, and there can be elongated opening like the three figures that you can see in the bottom. And each one of them has a different behavior. You see the bottom one, and for that matter, the graph that you can see at the top, this also shows that a shear wall structure and a RCC frame building, you can see the amount of strength that you have in a shear wall building rather than a RCC frame building. Now coming back to this thing, so if you have smaller opening, then this shear wall is behaving more or less like a solid wall, but you have to be very careful to design those beams, these beams which are linking these two parts. You have to be very careful, and there is a the design of these are very, very important, and the reinforcement into these linkings are too much. It demands very high reinforcement, I tell you. So it has to be very careful while designing this type of this thing. In the other now, Ankit, get back to the previous one. Yeah. Now see the moment also and the axial forces. As the things are getting separated, then predominantly the axial forces are much more predominant and the moments are less. But as they are closer to each other, moments are much more and the axial forces are much less. This is important to study while designing. Yeah. Next slide. Now again, base isolation. This is again a very recent phenomenon that we are all getting into it. Excuse me if I can have a drink, just a drink of water. Well, in zone, you must be knowing that in the entire country, in fact everywhere, there are several earthquake zones in our country now. Zone 2, zone 3, zone 4. Zone 2 is absolutely mild zone. Zone 3, where Kolkata and Kolkata is lying, is zone 3. Delhi, Gurgaon, northern India is zone 4. Assam is zone 5, and some parts of Bhuj is also zone 5, and there are other zone 5 also. Now, in a zone 5 situation, the earthquake forces are so very high. And for example, you are going to design a hospital building, which is termed to be a disaster shelter in Assam. Somebody is coming up with a project to design this thing. Now, with the recent development in the code and the provisions that you need to undertake in this in this scenario, the forces virtually it will become. I tell you, we are trying to practice this thing. Is virtually it's becoming undesignable. I tell you, the amount of force 9%, 10%, 12%. Yes, it is possible. It is possible, but the project is becoming economically unviable. So, as an engineer, you have to also understand the economics of the project. So, you have to understand that the project is successful from the economic standpoint. So, and this base isolation is a phenomenon. What Japanese are doing, because as you understand, the earthquake phenomenon in Japan is much higher than the rest of the world. They are practicing this thing for quite some time. Now it's becoming very common. It's in fact in many of the hospitals I know in Assam, they are now getting designed with base isolation. What is it? What is it? What is it? Now suppose, as I said, if you remember the first earthquake, the first slide in the earthquake that I have shown, that the ground is moving, and due to the inertia, you have the head at the original location. Now suppose if I say, if our building is sitting on some marbles, and there is an earthquake, what will happen? The building will also move. It will also roll. So try to understand, will there be any force into it? No. The forces, yes, there will be some forces due to the friction in the bearing, but substantially the forces will be reduced, and you can have a very economic solution. Although the price of these bearings are pretty high, but that too, these prices are not that high, which will influence your economics of the structure. So this is what will happen if you look into this base isolated structure, the second figure. This is where we are putting the base isolations at the foundation. Let the ground move, let the structure stand at its own location. You will find virtually no forces, no deformations or in any force into this building structure. So the design is primarily dead load, live load. There are some amount of forces has to be taken for the lateral load. You cannot have an absolute zero, but there is a considerable amount of lessening of these forces by virtue of this. A typical bearing is shown down there. Now, this is the phenomenal. If you remember the first thing, the first slide that in the earlier slide that I have shown, the atmosphere Calcutta, that the bridge. This is a kind of bearing that has been put underneath the bridge of that building, so that the building, even there's a force, that lateral force is coming, the building can sway, the bridge can sway, all are independent, nobody is affecting anybody. So that is the phenomenon that we have already taken in our city. So we must be very proud of that. So there, but now I virtually this ends my lecture. I hope you have all enjoyed this thing, and some of the damages, Ankit showed us some of the damages there. What earthquake? See the sorry, Ankit, the last slide.
Yes, yeah.
Yeah, see the mode of collapses of all these buildings. So these mode of collapses, there are soft stories below this building. You can see the soft stories, the crack pattern you see. So I have been into, when the last earthquake, massive earthquake came in Nepal, I have been traveling to various places, and I could see that well-designed building with well-framed building, the frame was intact. There are damages in the non-structural elements, but if you have a good frame structure, you need not worry too much. Need not worry too much. But if there are too many of mass redistribution, yes, it has to be seen that the mass is equally. There shouldn't be too much of a lump in one place. Shouldn't be a lighter in this thing.
Yeah,
So again, I hope okay.
Yeah, I was just saying, this is not to frighten you all. This is just to understand that if you design it properly, this all can be avoided.
Yes. So
And
again, everybody, I think we have now come. Now we have some of the slides more, right? One or two more. Yeah, very interesting slides. Sorry. Yeah, this is a mode shape, how a computer analysis, the simulation of a building that we have done already. It's a live picture, live project. It's a live project.
It's a live project which shows how a building behaves. It's a FEM analysis which we are using to show how building.
What is FEM analysis? Is finite element analysis. What is finite element analysis? Is all the elements that are finitely divided into parts, and the analysis is being done so that you can understand the stresses to the finest of the. That is called finite element analysis for a broader sense. There can be a 6 inches thick book on this FEM analysis. So don't get worried about it.
This is just to understand how it behaves before it happens anywhere. You can understand in the computer simulation how the building will behave under the loads. So, and it's just this video is not very clear, but
these are all simulations that happens.
Yeah, I think this video is somehow not working.
Okay, forget it.
The last slide which I will explain you is how this detailing helps to achieve.
Yeah, this is again very important in earthquake situation. Now, in earthquake situation, plastic hinges will, in adverse situation scenario, there will be plastic hinges, but we should avoid, as I said, the collapse. Now, how to handle this collapse? The concrete is not falling off. How to handle this? You see, the major thing that we must understand, that a beam column junction, a vertical and a horizontal junction, is very important. It should stay 90 degree even after the deformation. That is what we call as an elastic. We should not see, there can be, it can go into plastic zone, but for the time being, let's stick to our elastic design only. And I believe in keeping structures within behavior within the elastic zone. So to keep the things within the elastic zone, these detailings are adopted, especially in the columns. So especially you can see in the beam column junctions, there are links that are being provided, so that even after deformation, the angle between the beam and the column remain 90 degree even after deformation. That is the thing that you should always try. So if that happens, even in adverse condition, nothing will happen to your structure. So these are the typical details that we have shown, and to prevent the collapse in the structures and cracking in the concrete. Even there is cracking, it is not going to fall off. So this is very important. We should follow, and these are all from the book. So don't worry, you will just follow this code. These are come up with much more R&Ds from the from all our from throughout the world. So follow these details. I think your structure will be absolutely safe, not a problem. And these are simple details, not to be very complicated detail, but you have to practice these things. Yeah. So there it is. I think I could give you a little overview on how you should approach these loads into the structure, and from in the future, while handling projects, you anticipate how the things can happen, and I think you all will be fine. Along with this, with these things in your mind, you refer to any books, you refer to the codes, you will find absolutely simple to do the detailing, not a problem at all. Thank you for listening, and please, if you have questions, please. Give me a time for having some water.
Yes, thank you. I mean,
Yes, if you have some questions, you can just write it in the chat box, please.
I have eaten too much of a time, is it?
No, it's okay. I mean, it was very insightful and very important also for them to understand.
Thank you. Thank you.
You may please write down any questions that you have.
There's a question.
Yeah.
There's a question from. It's a very good question. Very good question. In order to avoid soft story effect, can we increase the column sizes in the ground floor? Yes, of course you can. Of course you can. But you know what happens? There is a dimension for your car to park. At times, if you can, please do this. Not a problem. But at times you may not be able to do this because a car size, we need to give a 2.5 by 5 meters. There, you can't increase the column size. But if you can do this, this is the best practice. Of course, this is the best practice. Good question. Very good question. Any more, please? Even if after this you get some questions in your mind, it is not an end to the whole story. If you have questions in your mind, send to your ma'am or to your email, to our email also. We'll try to answer as many questions as possible. Now, don't worry, even if you don't come up questions right now.
You can just wait for 5 minutes. Let's see if they have any questions. Otherwise, we'll wrap up.
But there can be. Again, this gentleman is. I must thank this gentleman, this Vinayak Samanta. It's good questions. Can you show me the question again? Yeah. Sorry, what is it?
How construction joint and expansion joints are placed in buildings, sir?
Yes. Well, there is a guidance in the code. that expansion joints are 45 meters, 45 meters apart. You provide ideally you provide at 45 meters, but these days you cannot afford to provide, because the gap of this expansion joint, is very difficult to provide, because from the earthquake standpoint, at times you will find out this gap comes to about a foot or so, which you cannot provide. So these days we design buildings even up to 70-75 meters. We have designed a building even up to 80 meters. These are difficult things to do, but while designing a 70 more than 45, 50, 60 meters building, one thing you must try to analyze there, the temperature load and the shrinkage load. Now, more the temperature difference, more this temperature difference, the shrinkage difference is much more vulnerable in a long building rather than temperature, because this is not a phenomenon I could have explained too much of this. But if you have any of you having a book called Design of Concrete Structures by Fintel, if you go into this and get into the expansion joint phenomenon, you will find absolutely clear what is the phenomenon that is happening. So providing an expansion joint, you can provide, best thing you can provide a 45 degree if your architect allowing you to do it. But I hope these days with the designs that are coming up, you cannot provide, because the more the expansion joint you give, there is chances of water leakage into it and all sorts of problems. The treatment of our expansion joint is a hell lot of a problem, and expensive also, because you need to provide an earthquake joint there, so that the two buildings, while sways, they can sway freely. So these are the things which you have to keep in mind.
Sir, just to add, the construction joints are given based on the way how the length of the building is, and based on the way we have how we have planned to cast our buildings. So there is no hard and fast rule for construction joints, but it's based on a lot of factors, and as it is not a permanent joint, so we can change it based on our usage.
I have a question.
Yeah.
The atmosphere which you have been involved into,
Yeah.
so the bridge which is 100-meter bridge above. So what type of a joint at the two ends have you used, and how?
Yes, ma'am, it's a pin joint. It's a pin joint, but we have provided bearing in there. There are 4 bearings supporting the main structure. Now, this pin joint, what has done, has damped down the entire lateral force to more than 50%. That is what we have done, and that has allowed the forces. The bridge can move in any direction by 10 inches in any direction, and so does the building does. So none of the building or the bridge is affecting each other.
And these also have those base isolators which you said.
This bearing is the base isolator. This bearing is a base isolator, acting as the base isolator. No.
The bridge and the main building.
No. In the building, no. There's no base isolation. There's no base isolation. The bridge is only sitting on a base isolator. That is the bearing. I think there's a gentleman who has given a question. Ankit, address this question.
Yeah, to protect the building from seismic effect, where do we place the dampers? Does damper affect stability of the building during fast winds?
Yeah.
So see, this position of dampers, like we have used in 42, was based on how we analyze the building and where we get the maximum forces due to lateral loads, and based on also the location where we can put a MEP floor where we can accommodate a damper. So it's basically based on the curve of the force that we get through a analysis, so that where the maximum force is there, we can place a damper and reduce the forces. And yeah, it's obviously for high-rise building like 42 and other things.
Okay, can we assume that for a particular place for the force to be maximum, will that be at the foot level of the building, or it can be at the any point of the building?
Ankit, address this.
Yeah, the base shear will be maximum at the foot, but the displacement will be different at different levels. So that we need to check
See,
based on the analysis result.
yeah, that's where let me tell you. Now, as I said, that the basic difference between an earthquake and a wind is that one is an stress-induced forces, and the other one is the direct force. Now, while doing an wind, it's the serviceability that matters you. So that the deflection or the acceleration is maximum at the top, and while you have in earthquake scenario, the acceleration is maximum at the bottom from the earthquake. So wherever the acceleration is the more, that I as a very simplistic way, I follow this principle that wherever the maximum acceleration, you put your dampers there.
And are these dampers basically custom manufactured, or they are
Yes.
standard suddenly?
Now, ma'am, this is becoming so frequent in use. One of the damper manufacturer down here, they are to some of them are standard manufactured, but you have to produce them the load and what is the amount of damping that you want to understand, that has to be given to them. What is your vertical load that needs to be taken? How much you want that thing to be moved? What is your lateral load? How much, say for example, you have a 500-ton lateral load, you want to bring it down to 250 load. So you provide them all these features, they will design and bring back to a solution.
And what are these materials generally made up of? The bearings?
It's steel, basically steel and rubber, and Teflon, and what is the material that Ankit we used in specific material that we used in
PTFE was the material which we
yeah,
used in
PTFE.
for
PTFE is the
the
material for this
atmosphere.
atmosphere. Yes. It's called the atmosphere bearing that we call it's called erratic quake bearing. Erratic quake.
Can you place the damper at the foot of the lateral effect forming tunnel wind system at the top?
In wind situation, we normally put at the top, and
And in this
in
case, we
earthquake
put
situation we put at the bottom. As I said, as a principle, I follow this thing that wherever the acceleration is more, we provide the damper there.
This is another question. Please explain significance of tributary area while calculating wind load.
Yes, absolutely fine. This is the while calculating the wind forces and putting them into some point of time, some point of your structural member is absolutely fine. That this is the way that you should do, putting the contributory. See what happens. The infill wall acts as an arch, and the wind that is coming onto this arch is transferred into the beam and the column to the sides. So this is absolutely okay with calculating these forces. Not a problem. Not at all a problem. Not at all a problem. Please go ahead and do it. We do it also like that.
Though it is not that significant to earthquake, but to wind effects, if we talk about the tunneling effect, if the architects actually take into account of making some spaces inside the structural buildings so that the wind
Yes.
can pass through it, so
Yeah.
would the tunneling effect, and the movement of these things be taken care of to some
Yes,
extent?
ma'am. Yes, ma'am. It's all because these are called local design that we have to do. It will help in the total deflection. It will definitely, with punctures at some points, will help in the total wind forces and the total deflection at the top. But while passing through these holes, there will be the velocity of the wind will be very high. So the fixtures, the things that are projecting out into this tunnel can be affected with this thing. So you have to careful in designing those local elements only, not to worry about. This will help, of course, in designing your total building. Hope I have answered your question, right?
Yeah, yes, sure.
Good, I enjoyed doing this thing. And it's too long, right? More than 2 hours.
We look forward to, I mean, having more sessions with you in future.
I'm always glad to do it. Once this is over, our team can visit your college also, not a problem. We can be there.
Right
And
now, because of the pandemic, I do not know when we are going to resume.
yeah, I understand that. But
we are
this can
having
happen.
online classes, we are having online examinations, we are
Yes,
having online experimentations, everything online.
No, we are also having online meetings, also design coordination meetings, So we are all getting these days acquainted to this, and more like this will happen. But whenever there is something, especially, I would say my advice to the final year student. My advice to the final year student: don't get bogged down to service. Don't get bogged down. First of all, I would say, whatever you learned till this time, for long 4 years, assimilate inside. Try to find out what of the subject that you have enjoyed in these 4 years. Cultivate that thing more. Add more books into it, and ask questions to yourself. And if you don't have a question, to some expert, we are there to answer you. But never waste your time in I'm not getting this job. Job will come, job will run after you at some point of time. Don't get worried at all. But whatever, but first of all, one thing that again I'm saying, be proud to be a civil engineer. Be proud to be a civil engineer. You always compare to people that this gentleman has studied this thing, but no, you should be proud to be a civil engineer, and you should enjoy what you have studied, and you should accumulate what you have studied, read further, and do what the best thing as an engineer should do, and should do to build the nation. I think that's my message to you all, and my message to the first year students also. See, the 11 and 12 that we have studied, I still tell my people, go back whenever there is a problem. Go back to 11, 12. Take out the physics and the maths book. Whenever there is a problem, take out those two books and then read it. So the basic physics and the basic mathematics, that whatever you have studied in 11, 12, that will pursue throughout your career. So, and think, be creative. Don't get into too much into studies. Yes, of course you will study, but as I say, close your eyes and think how things behave in life, not only in engineering but other things also. How things behave in life. See, at some point of time, all these things will come after you, run after you. Don't worry about now. Things will be absolutely okay. Don't get panicked about it also. But make though whatever you are learning, enjoy the learning. That's what I will always say. Not all the subjects you will enjoy, I understand, but try to find out which of the subjects you like and get into that study. Enjoy that study. That's my message to you all.
I think they don't have any other questions right now.
It's fine.
In case they have, they will send it to me.
Yeah, of course. Of course. Yeah.
It was very insightful and very good session.
Thank you.
know I have enjoyed it personally. I am sure the students and other faculties also have enjoyed it. We look forward to have many more sessions like this.
Thank you very much.
Maybe I'll have some chat later on with you with regards to some scope of doing some research works also, as if you are already
Fantastic.
doing, so we can
Fantastic.
jointly work on
Fantastic.
it. No issues.
Fantastic.
In any case, in the fourth year, we have students to do some project work, so they can
Okay,
closely
fine,
work with you
fine,
also.
fine, fine. We have so many of projects in our hand. If
Yeah,
we can have people, we can help us out. Will be wonderful. Will be wonderful.
great. So
Great,
we'll
great.
forward.
Yeah, yeah.
Thank you
Thank
so
you,
much.
thank you,
Thank you,
thank you.
Ankit.
My pleasure. My pleasure.
Yeah, thank you so much.
Thank you, ma'am.
Bye, bye.
Students, please stay back. You need to fill up the feedback form. I'm just sharing it, sharing the link. Just hold on. You please request it to share, I mean, fill in the feedback form. Those who have filled up can leave, no issues.